Alright, this video is over probability rules, which of course has double meaning because A, we're going to learn about the rules of probability in this video, but we're also going to learn about how probability rules. It is really the most important thing in statistics probably. I'm just going to go ahead and say it. Now please, if you are taking guided notes, please make sure you're using the guided notes for probability rules. If your guided notes is over randomness and probability, you need to go back to the previous video that covers randomness and probability. This video is for probability rules. Alright, so before we move to talk about the probability rules, let's make sure we talk about a couple terms. The first thing we need to understand is what is a probability model. A probability model shows all possible outcomes and the probability of each outcome. You could do this in a diagram or in a table. Okay, now we call this the sample space. The sample space is simply everything that can happen. So the sample space, that's kind of a weird term for this, but it's again every single thing that could happen for your random event. So I give you actually five examples here. So for example, tossing a coin. When you toss a coin, here is a probability model. So again, it shows your outcomes. There's only two outcomes, a head or a tail, and it shows the theoretical probability. So the theoretical probability for a head is 50%, 0.5, and for a tail, it's also 0.5. Now, this is another type of diagram. It's more of like a tree diagram. So when you roll a die, there are six outcomes: 1, 2, 3, 4, 5, or 6. And again, I just wrote next to each outcome the probability. So the probability is 1/6 for 1, 1/6 for 2, 1/6 for 3, and so forth. In fact, this is a situation where we have equal probability. All outcomes have an equal probability, 1/6. Okay, now here's another example right here. And I was a little in the Thanksgiving mood here, so I said, what are you going to have for dinner at Thanksgiving? You can have turkey, you could have ham, you could have both turkey and ham, or you could have neither. Now, that's theoretically kind of hard to figure out, what percentage or what proportion of families in the United States have turkey. Well, again, I'd have to look that up to kind of figure this stuff out. So I kind of left these blank, but I just wanted you to get the idea of this is everything that can happen. So if I think about my dinner table on Thanksgiving, there could be turkey on it, there could be ham on it, I could have both, or I could have neither. So those are the options for what could possibly happen here. All right, now, and then here's another example I thought about. If a family has two children, if a husband and wife or have two children, what could happen for those two children? Well, here they could have a boy and a boy. They could have a boy and a girl, They could have a boy first, then a girl, or they could have a girl first, then a boy. So then I thought, let me erase this so I have some room here. I thought about, this is actually fairly simple to walk through the theoretical probability as long as you assume that there's a 50% chance of a boy or a girl. So if I want to have a boy and a boy, that would be 50% for the boy times 50% for the girl. So boy and then another boy would be 0.5 times 0.5, or 25%. Girl would be 0.5 times 0.5 as well, or 0.25. Boy girl, that'd be 50% for the boy, 50% for the girl, and then 25%. And then girl boy would be 50% for the girl, 50% for the boy, which again would be 0.25, 25%. Now again, this is assuming independence, which means what you have the first time around has no impact on the second time. Okay, and then I came up with another example here. Let's just say that you are running a race, and when you run that race, you could win, you could lose, or you could technically come into a dead complete tie, a complete finish where it's a tie. So maybe you're pretty good at running, so you think there's a 60% chance that you win, there's a 39% chance you lose, and there is that rare 1% chance that you come into a tie. Okay? Now, those are probability models. Again, every option is listed and the associated probability. All right, notation. Once again, I talked a little bit about this in class, but remember we use P for probability. So we say the probability of getting a tail is 50%. The probability that I roll a 4 is 1/6. The probability that I win a race is 30%. Again, just know that P is for probability. This does not mean P times win or anything like that. This is just notation for talking about the probability of an event. Now, the third term is this term event. I've talked about this event. I've used this word event, but understand that event is a subset of the possible outcomes. So let's kind of go back to rolling a die, right? When you roll a die, Individually, you can get a 1, a 2, 3, 4, 5, or 6, but an event could be something like rolling an even number. Now, there are actually 2, 4, 6. There are 3 of the 6 outcomes that are even, so the probability would be 3/6 or 50%. Or I could say, what is the probability you roll a prime number? Well, 2 is a prime number, 3 is a prime number, and well, my marker's not working here all of a sudden. Sorry about that. And 5 is a prime number. 1 is not a prime number by definition, by the way. So again, 3 of the 6 numbers are considered prime. So that's an example of an event. So it's kind of a combination of several things. Okay, now when we think about probability rules, there are kind of a couple small ideas, and we call these rules, but there are two really main large ideas, which I'm going to talk about in this video. The first large idea is, am I finding a probability of a simple thing? When I say a simple thing, am I trying to find the probability of event A? Just try to find the probability that A happens, okay? Or am I trying to find the probability of A or B? If I try to find the probability that A happens or that something else happens, B. Or what about the probability of A and B simultaneously happening, okay? And I'll talk a lot more in detail about that in a moment. And the other main idea is maybe I'm trying to find the probability of multiple events happening after each other. So I need something to happen and then something else and then something else. I call this the domino effect. And again, I'll talk a lot more about that shortly here. All right, so here's our 4 main small ideas. So main small ideas, it's kind of a... Anyway, 4 small ideas. These are, again, rules. I think of this as more common sense stuff, but I do want to go ahead and explain it. So the first is that the probability of any event, I'll use A to represent any event, the probability of any event has to be between 0 and 1, inclusive, which means I could equal 0 or I could equal 1 or 100%. So all probabilities are between 0% and 100%. As a decimal, that's 0 to 1. There's no way you can have a negative percentage chance, or you can't have over 100% chance for something to happen. So that's the first common sense rule. The second rule is that the probability of a sample space is always 100%. So S is the sample space. This is basically saying if you add up each outcome's probability, you must get 100%, or again, as a decimal, that would just be 1. So if I'm thinking about rolling a die, there's a 1, a 2, a 3, a 4, a 5, 6. There's only 6 things that can happen. If I add up all 6 probabilities, I have to get 100% because something has to happen. So if you forgot something, then you probably didn't get 100%. So again, the idea is the probability of everything must add up to 100% for a particular random event. All right, the third rule is that some outcomes are equally likely. For example, rolling a die. If you roll a die, each outcome is equally likely. 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. Some outcomes are not equally likely. Okay, for example, winning a race, losing a race, or tying a race, those events or those probabilities could all be different. So it's just a very simple common sense thing that sometimes you could have outcomes that are equally likely. All right, the fourth rule is called the complement of an event. This is the event not happening. So the complement of an event is the probability that that event not happens. All you have to do is put the word not in front of it. So we use this little C here for complement. So if A is the probability of any event happening, if I put this little C up there as like a subscript or a superscript, then that is the probability of not A. Again, it's just not A. So if you say, what's the probability that I get a 2? Well, the complement would be not getting a 2, so anything other than a 2. So to do that, all you got to do is take 1 minus the probability of A, and you would get the probability of it not occurring. So if there's a 1/6 chance of getting a 2, the probability I don't get a 2 would be 5/6. Pretty simple. But be careful describing this. I like to use the following example. If I said, what's the probability that you get straight A's? Okay, so I can't spell straight A's, okay? So the complement would be not straight A's. Now, I don't mean that you get no A's. So you have to understand, the opposite, the complement of straight A's would be at least one class you don't get an A in. Because the moment you don't get an A in one class, you no longer have straight A's. So some kids just say, well, that means I have no A's. Well, no A's is something completely different. No A's means you literally got no A's. So the complement of straight A's is you simply have not straight A's, meaning that maybe one class you did not get an A in. So just be careful. All we got to do for a complement is put the word not in front, and it makes it really simple. Okay, I wanted to look at a common example. I use this example a lot in class, and we'll use this a ton, so I wanted to make sure I emphasize it today in this video. And that idea is rolling two die. So first off, when you roll two die, maybe a green die and a red die, this is a nice chart that shows us everything that could happen. So there are 6 outcomes for the red die, 6 outcomes for the green die. 6 times 6 is 36 total outcomes, shown nicely in this chart. And you can actually see all the different outcomes happen. Now, when you roll two die, we like to add up the sum of the dots that we see. So here are the possible outcomes. So I'm trying to show you an example of a probability model where you have all the different options shown. So when you roll two die and you're looking at the sum of those two die, here are our options. So let's figure out the probability. What's the probability that I roll a sum of 2? Well, there's only one way that can happen. And that would have to be me rolling a snake eyes, single digits, 1 1. So there's only 1 out of 36 ways that can happen. And then likewise, to get a 12, that would have to be a 6 6. And there's only one way that can happen, so that is also 1 out of 36. Now, how can I get a sum of 3? Well, I can get a 2 and a 1, or a 1 and a 2. Again, because I have two different die, that could be a 2 on the red and a 1 on the green, or a 1 on the red and a 2 on the green. So there are 2 out of 36 ways that can happen. And then you see a little bit of symmetry here, because to get an 11 would be the same thing. A 6 on the red, a 5 on the green, or a 5 on the red, 6 on the green. So there would be 2 out of 36 ways to roll an 11. To get a 4, that would be a 3 and a 1 and a 3, or a 2 and a 2. So there would only be 3 ways that can happen. And you see them right there, 3 ways that can happen. So that's 3 out of 36. Okay, and you have to understand that it's some kids say, well, wait a minute, can I get a 2 and a 2? Well, no, there's only one way to say 2 2 2 2. If I try to write 2 2, it would look the exact same. So that is why 1 and 3 is different than 3 and 1. But 2 and 2 is, well, 2 and 2. So there's 3 ways that can happen. To get a 10, here you can actually see them. 6 4, 5 5, or 4 6. So those are the 3 ways out of 36 that you can get a 10. 5 4 1, 3 2, 2 3. 1 4, so there's 4 out of 36 ways that you can get a 5. 4 out of 36 ways for a 9, and you can see them in the chart there. I don't want to keep boring you by going over these. 6 would be 3 3, 2 4, 4 2, 5 1, 1 5, so that'd be 5 out of 36. Same with an 8, 5 out of 36. And then 7 is actually the most common. There are 6 ways to get a 7, 6 out of 36. You can get a 3 4, 4 3, 2 5, 5 2, 6 1, 1 6. So a 7 is the most common sum that you could have when you roll 2 die. So all of those, if you add all these up, it does add up to 36 out of 36, or 1, which shows that my one of my rules is true. And let's talk about a couple events here. The event that the sum is even. Well, that would be a 2, 4, 6, 8, 10, 12. So if I add those up, that'd be 1, 3, 5, 5, 3, 1. That adds up to 18 out of 36 ways that I can get a sum that's even. How about the sum is prime? I'm going to grab a different color for prime here. Prime would be 2, 3, 5, 7, and 11. So that'd be 2, 3, 5, 7, 11 are my prime numbers. 9, 10, 12, not prime, 6, not prime, 4, not prime. So again, that would be, let's see, I've got to figure those out. That'd be the 1, the 2, the 4, 6, and 2. So it's 15 ways that you could have a sum that is prime. How about a multiple of 4? Okay, well, multiple of 4. So let's see here. That would be 4 is a multiple of 4. 8 is a multiple of 4, and 12 is a multiple of 4. So that'd be the 3, the 5, and the 1. So that'd be 9 different ways that you could have a multiple of 4. So again, those are events. Those are examples of events. Now, what I want to start talking about here is this idea of prime and odd. Now, and means both, right? They both have to occur. How many different numbers are prime and odd? So 2 is prime but not odd. So 2 is out. 3 is prime and odd. So that's a good one. Let's see here. 5 is prime and odd, so that's good. 7 is prime and odd. And 11 is prime and odd. So I'd have to add up those outcomes, and that would be 14 out of 36. Now remember, there were 15 primes, but all of a sudden 2 is no longer odd. So 2 is prime but not odd, so I would not include that one option, which is why it drops to 14 out of 36. Okay, now or means one or the other. Okay, or both. So you have to understand the word or actually means three things. It means that it's prime, or it's odd, or it's both. So I got to go through here and think, okay, 2 is prime. It's not odd, but it is prime, so that counts. So 2 counts. So I'll put a little star there. 3 counts. It's actually both odd and prime, but it definitely counts. 4 is not prime, nor is it odd. 5 is prime and odd, so that counts. 6 is not odd. 7 counts. It's both. 8, no. 9 counts, right? Now 9 is not prime, but it is odd, so 9 would count. 10 would not count, it's not odd. And it's not prime. 11 would count, it's actually both prime and it's odd. So again, when you're talking about or, you're talking about prime, or odd, or even both. If you have both, you're going to count there as well. So that would be adding all those together, which would be 19 out of 36. If you want to take a time to actually add those up, feel free to go ahead. So I thought that was a nice example to kind of show you what can happen when you roll 2 die. That's something that we're going to talk about a lot in class. But it also helps us get ready for what we're going to talk about next, which is the first big idea. So big idea number 1 is basically talking about 2 events. So we have 2 events, A and event B. Now, what I want you to think about here, and we're talking about big idea number 1, we're only going to do one thing, right? So we're talking about 2 different things that can happen, and we're looking at those 2 events. The key thing here is that we could talk about the probability of event A happening. Okay? This is the probability of event A. And you have to understand that, anytime event A occurs, I'm going to count it. That's going to count as event A. Would be event B, trying to find the probability of event B occurs. That makes sense. And now this is and. Now a couple things about and. And means both, right? You got to be very careful with that word and. I mean both. Both A and B must both happen simultaneously. O-U-L-Alt-tain-E-S. I'm sure I spelled this wrong. I'm terrible at spelling simultaneously. But again, you guys get the idea, right? Now, in statistics, we have a symbol for and that is an upside down U. That is the symbol for and. So you may see that symbol. That means and. But keep in mind both. A and B must both occur. We also have A or B. Okay, now the statistical symbol for or is a normal looking U, right? So on a U, basically, is the symbol for or. Now, when we say or, we mean A or B or both. You have to keep that in mind, that the or actually means 3 things. It means A occurs, B occurs, or even both occur. Okay, so you got to understand or includes everything. It's kind of important. Now, a big term that comes up in this big idea number 1 is mutually exclusive. Mutually exclusive is 2 events that can not occur at the same time. This is what we mean by mutually exclusive. 2 events that cannot occur at the same time. Basically, the probability of A and B, notice I use that upside down U there for and, equals 0, meaning that they cannot occur at the same time. So the probability of both A and B occurring becomes 0. That is what we mean by mutually exclusive. Now, big idea number 1 is really simple, but I really want to make it easy through an example. So I came up with a little example here. So let's just say we're at the zoo and we're looking at bears, and we notice that there are 2 kinds of bears. There are black bears and there are brown bears, but there's also male bears and female bears. So I made a little chart here to show you about the bears that I counted at the zoo. And you see my chart that shows that there were 14 total black bears, 19 total brown bears, and 16 males, 17 females, 33 total bears. You get the idea. So to understand idea number 1, I really want to do an example here that's so simple to understand. All right, if I said, hey, what's the probability that you go to the zoo and you randomly see a black bear? Well, you say, okay, well, there are 14 bears that are black. That means 14 bears are going to successfully make me happy because I want to see a black bear out of 33. There's your answer. That's it. That's how simple it is. 14 out of 33 bears are black. All right, what about male? Okay, well, male. Well, I want to see a male bear, so I'm going to know that there are 16 males in the zoo. out of 33 total bears. How easy is that? Oh my goodness, so easy. Okay, now this next one is pretty easy as well. Black and male. So this is black and male. Remember that upside down U means and. So this is specifically how many bears are both male and black. So that's looking right here, right? These are the 12 bears that are male and black. So again, that's pretty easy as well. 12 out of 33. I love these charts. Charts like this make probability so simple. All right, now this is or. Now this is a little bit tricky. Here I have to teach you something. You got to think a little bit about here. Okay. So, the probability that it's black or male. Okay, so let's see here. It could be black, or it could be a male, or it could be both. So let's see here. How many bears are black? Well, there are 14 bears out of 33 that are black, okay? Or, so I'm going to add, what about the male ones? Okay, well, there are 16 bears that are male. So that's 16 out of 33. Now, I'm actually not done there for a really important reason, okay? Because black and male are not mutually exclusive. 12 are both. And that's a problem here. Because these 12 bears that are both black and males, I counted them here. They were counted amongst these 14 bears that are black, right? But they also got counted here amongst the 16 bears that are male. Now, those 12 black and male bears deserve to be counted, but not twice. So I do have to subtract away the 12 out of 33. I'm not throwing those bears away. I just don't want them to be counted twice. They got counted as part of the 14 that are black. They got counted as part of the 16 that are male, but I don't want them to account twice, which is why I got to subtract them away. So that leaves me with, when I do my math here, I already got a common denominator, so 14 plus 16 minus 12 gives me 18 out of 33 bears. Now, these 18 out of 33 bears are black or male or both. All 18 bears are accounted for there when we think about this, all right? So hopefully that makes a lot of sense. Now, I'm going to come back here for a second because I want to add something to this rule, right? This is a really important rule. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, I'll move this over so you can see it a little better. This is called the addition rule. This is huge. I love this rule because it involves or and it involves the A and the B. But this is a really important rule to remember, that if you're trying to find the probability of A or B, you need to include A, you need to include B, and you got to subtract away both. Basically, you're subtracting away the overlap. It's not that you're getting rid of those bears. You just don't want them to be counted twice, because some of these bears that they were counted here as having A, they were counted here as having B. You just don't want them to count twice. That's why you subtract them away. So we're going to do a lot of examples with this in class. But hopefully, you know, that rule, this big rule here, and this chart about the black and the male bears really helps make sense. I really hope it does. Hopefully that's pretty easy to understand. We'll talk a lot more in class about that, but that's really the big idea for number one, is that really important rule that you understand there. Okay, now big idea number two. Big idea number two says calculating more than one event, meaning one event occurs and then another event. I call this a domino effect. So when we're talking about big idea number two, we're not talking about one thing happening. We're talking about something happening and then something else happening. Now, this is very different than and. So I want to emphasize here that and then, the phrase and then, is very different than the phrase and. And by itself means both. Both at the same time. And then doesn't mean the same time. And then means one thing happens and then something else happens. So this is very, very important that you understand the difference between just saying, hey, both versus and then. Okay? So let me give you an example. Black and male. That's an example of both, because I'm looking for a bear that is black and male. A bear, one bear. And then would mean, hey, what's the probability that I randomly choose a bear that is black, and then I choose a second bear that is black? That's the idea of saying and then. I'm actually doing two things. I'm not just looking at one bear. Okay? Here it's really important to know if the events are independent, meaning does the outcome of one event affect the outcome of the next? Okay? Let me give you the first example. If you're rolling a die twice, And I say, what's the probability you get a 2 and a 6? 2 and then a 6. Well, the probability I get a 2 is 1/6. And then I need to get a 6, which is also 1/6. Now, when you roll a die, you have independence because the second roll doesn't remember what happened the first time. So the outcome of the second roll is not impacted by the first. So this right here is the probability of rolling a 2 and then rolling a 6. So the answer to that question would be 2 out of 36. You just multiply. So multiple events, you must multiply. Keep that in mind. Now here's a second example where it's not independent. Here we have 10 kids and we're picking 2 boys. So there are 3 boys and 7 girls. So now I need a boy and then a boy, right? And then a boy. So the first boy, I have 3 out of 10 to choose from. For the second boy, because I already picked a boy, my second choice is now affected. That means there's only 2 boys out of 9 total kids. So I have 6 out of 90. So that is how you would solve that. So you get the idea of independence. So if your second outcome is affected by the first, all you got to do is think about it. Dies, it doesn't matter. They don't have a brain to remember. But when you're picking boys and you got to pick a different boy that second time, it does matter. All right, here's the final example to try to hit home this second big idea. So imagine I have a jar of marbles, 3 red, 10 green, 2 yellow, 1 blue. If I pick out 2 marbles, right, one and then another, right, I'm going to pick out one and then another. So I'm trying to emphasize that I'm doing 2 things by using that phrase and then. So I'm going to do no replacement, which means I'm going to take that one out and I'm going to keep it out. I'm not going to put it back in. So I need 2 reds. So that means the first time I reach in, I have 3 out of, how many, by the way, there's 16 marbles here, right? 10, 3, 2, 1, 16 marbles. So 3 out of 16 for that first red, and then I already got a red. I didn't put it back, so there's 2 out of 15 marbles left that are red. So multiply that out and you get your answer. That's pretty easy, right? Okay, I need 1 red and 1 green. Well, when I reach in the first time, I could get 3 out of 16 that are red. And then I reach in for that green, there are 10 out of 15 that are green. But there's another way that can happen, right? Because I did red and then green. But I could also do green and then red. Now that is a different scenario, so let's walk through that. Green would be 10 out of 16 green. Times, now for red, there are 3 reds out of 15 marbles. Remember, I did not replace that first marble. Now, both of these look the same, 3 times 10 on top, 16 times 15 on the bottom, but they are different in terms of how that could actually happen. So I'd have to calculate this first, and then calculate this and add them together to get my probability. Again, we're going to practice a lot of this in class, but we need you to understand that idea. 2 blue. Okay, so the first time I need to reach in and get a blue, there's 1 blue marble out of 16. And then I did not put it back, so now there's 0 out of 15 blue ones. So basically the probability of getting 2 blues becomes 0. It can't happen. There's only 1 blue in there. Now this time around, I'm going to replace. This time I'm going to pick out that first marble and then put it back. So now to get 2 red, that would be 3 out of 16 times, well, 3 out of 16 because I put that marble back. So that means the second time all 3 red ones are in there and all 16 marbles are in there. So you will get a slightly different answer. 1 red, 1 green. Well, once again, that could be green first, then red, or red first, then green. You do have to take order into account here. So there's 10 out of 16 green, and then you put it back in because you replaced it, and there are 3 out of 16 red. Plus, because there is another option, you could get 3 out of 16 red first, and then your 10 out of 16 green. But my denominator stays 16 because I'm putting the marble back. Now, 2 blue would be possible here because that would be 1 out of 16, and then you put that marble back, so you need 1 out of 16 again. So that would be 2 out of whatever 16 squared is. So you get the idea here. Now, what I'm trying to emphasize is the 2 big ideas. The first big idea is you're only doing one thing. You're looking for one bear, but you're looking for a male, maybe you're looking for black, or maybe male or black, male and black, but just looking at one bear. The second main idea is you're looking at 2 things. You're looking for one thing to happen and then another. So you have multiple events, which means you multiply. But you got to keep in mind that you got to be careful how you multiply. Doesn't matter. Do those events have independence or not? Does that marble in the jar get taken out and I keep it out, or do I put it back in? All those kind of things matter. So remember, the main idea I'm trying to get across to you in class is you've got to use your brain to think about probability. But big idea number two is that literally two or more things are happening, one after the other. That's why I call it a domino effect, one after the other. Or big idea number one is there's only one item happening. You're looking at one bear. You're just looking at maybe you don't care if it's black or if it's a male. You don't care if it's a brown bear or a male bear. Or maybe you want a brown bear and a male bear. It's got to have both. But again, I'm talking about both, not and meaning two things, both things happening at the same time. So we obviously have a lot to clear up in class. We will talk about a lot, but I need you to get these notes started to understood. That way we could talk a lot more in class about it. All right, hope the probability rules convince you that are a couple rules of probability, but also we will slowly learn that probability does rule.